So these are your Chapter 1A notes. Since this is your first lesson in the flipped classroom for Algebra 2, I just want to go over a few things in this video. First of all, I strongly suggest watching the video and listening to the video at the same time. If that means getting some earbuds or making sure that you have the volume up. I did find in my Algebra 1 last year, many kids were only watching the slides, not listening to the volume, not fully engaged. You only get half the information that way. So in order for this flipped learning to work, you have to be a fully engaged, active learner on your own time. So remember, the benefits of this is that you're not sitting at home completely frustrated, trying to do homework that you sort of know, but you have questions on. So I'm giving you the lecture part. I'm giving you all the answers. I just need you to have your full attention while doing so. And so if that means that you may have to rewind, you may have to pause to keep up. I go a little bit faster. I don't pause as if you're in class. So if you miss something, you just need to rewind or pause and go back. I try to compare it to a YouTube video that you watch for instructions. If you've ever watched a YouTube video and you really want to know how to do something, whether it be a skill or a song or a recipe that you're trying to follow, you will pause it, you'll play it back because it's important to you. So treat these the same way. So in Chapter 1A, you should have a note outline along with you to follow along with these notes. We're going to go over a bunch of stuff from Algebra 1. So I don't really go section by section here to help with the time factor so that we can spend more time on more difficult Algebra 2 concepts. So I call this section 1A because I took 2 or 3 different concepts and mixed them together. So in this section, we're going to cover number sets, which is really important. We relate to these all year long. And so if you don't understand what rational means or irrational means, it's a lot of vocab. So we use it throughout the year. And if you don't know what I'm referring to, it makes the math that much more difficult. And then just basic solving equations, some simple equation solving, get you back into that mode. The whole no CCSS, that's for me. That just basically says that this is not a common core state standard, but however, I deem it necessary for you guys. So even though there's no code in Algebra 2, because these are more Algebra 1 concepts, but to just jump in without them would be difficult. So I have this nice Venn diagram here, and the entire rectangle involving the mint green and the yellow rectangles inside it is the set of all real numbers. So I have the name real numbers listed above the set, and then I have the actual abbreviation that we use to denote real numbers, and it's a capital R for real numbers. Real numbers are all the numbers that you've studied so far. We are going to get into some other sets of numbers this year, not quite yet, but the other set is this little splatter mark here, and it's the imaginary. I just made it a splatter mark because I feel like it's more alien. So completely separate. It could be a circle, it could be a square, but it's the imaginary numbers, and they're denoted by IM. We'll talk about those later, but you cannot be an imaginary number and a real number at the same time. There's kind of a contradiction there. So completely separate from each other. Within the real numbers, every real number has to be classified as either a rational or an irrational. So for that, I divide that rectangle in half. Now I know it's not truly in half because I wanted to show you more subsets within rational. So I don't want you to think the rational numbers, there's more of them. There's infinite supply in all of these. So it splits it, and there's some numbers that are rational, and we use Q for rational. I believe the logic behind that is that we already used R, so they go to the next letter. And irrational would be I. Within the rational numbers, these are more of the numbers that you studied in Algebra 1. So these would be your natural numbers, your whole numbers, and your integers, and then rational numbers. So within that set, there's little subsets. And so just to distinguish what they are, the natural numbers, there's an infinite supply of natural numbers, but within the natural numbers, these are the naturally occurring numbers. When you were 2 years old and you were counting, it started with 1. Then you went to 2, to 3, to 4, on and on and on. And so dot, dot, dot means that it continues to positive infinity going up in whole number increments. You don't start counting with 0, you started counting with 1. Within that set, that entire natural numbers, which was n set, falls within the whole number set. So when it's a subset, that orange circle is inside the yellow circle. That means that all of those numbers are included within the whole numbers. But in addition to those numbers, we add one more number in the whole number set, and that's 0. So I'm only going to put a 0 in the yellow because 1, 2, 3, 4, on and on and on are already in there. So 1 is a natural number, but 1 is also a whole number. 3 is a natural number, but it's also a whole number. But 0 is the only one that's a whole number that's not a natural number. So it's kind of natural numbers we'd call a subset. Within the integers they give z. I have no idea why. But for integers, that's all of the natural numbers, all of the whole numbers, and then the negative matching whole numbers. So I'm not going to write down 0. I'm not going to write down 1, 2, 3, and 4. I'm going to do ... -3, -2, -1. Again, no decimals, no fractions, nice whole number increments, but now the integers, what they add are the negatives. So it includes the positives, it includes the negatives, and it includes 0. But the only difference between whole numbers and natural numbers and integers is the negatives. The final set, the biggest set, are all the other numbers that are nice numbers. Rational is reasonable. When people say that you're being rational, you're thinking straight. Irrational thinking is you're not thinking so straight. So think of the numbers as well. A rational number are nice numbers, sort of. I know they're not your favorites, but they're nice fractions and nice decimals. So what I mean by that, a nice fraction is 1/2 because it's a terminating decimal, 0.5. A nice number is 1/3, and its decimal is repeating. So rational numbers are the whole numbers, are the natural numbers, are the integers, but it's also these other sets. So terminating, that means they end, and repeating. So these don't end, but they have a nice pattern. Decimals. If the decimal terminates, it can be written as a fraction. If a decimal repeats, it can be written as a fraction. So we could actually add to this list fractions. Fractions that terminate as a decimal and repeat as a decimal. That's pretty much every single number that we've had so far. You've been exposed to a little bit of irrational numbers. The most famous irrational number that you guys have been exposed to is pi. Okay, never ends, never repeats, goes on forever, never, never. So it's a non-terminating decimal. And so it's irrational. It's ugly to work with. And then other numbers that are really ugly to work with are non-perfect roots. If they're not perfect, they're not going to be a whole number, and they're going to go on forever, never, never. Not repeating, not terminating. So these are your non-repeating. And non-terminating. They do not end. They do not repeat decimals. Oh, sorry, my board's acting up. All right. Give me 1 second. All right, so this first example, we're just going to practice what we just put on the graphic organizer on the last page. We're going to name the sets of numbers to which each number belongs to. You name all the different sets. So if you look at number 1A, it's negative. So the negative tells me we're either dealing with integers and rational numbers or just rational numbers, depending. Rational numbers can be negative as well. So negative 2/3 is not a whole number. So therefore, it does not qualify as an integer. It's just a rational number. So I'm going to put a Q for rational numbers. If you want to write rational underneath that until you learn the actual abbreviations, that's fine. 9.9999 dot, dot, dot. They can use dot, 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 or they could have put just a little bar over the 9, but the dot, dot, dot tells me that pattern repeats. And so this is a repeating decimal. And so therefore, this is a rational number as well. It's not a whole number, so it doesn't qualify as any of the others. Square root of 6. If you punch square root of 6 into your calculator, it is not perfect. And so it's going to go on forever and ever. No repeats, no termination, so it's irrational. And the square root of 100, when you put that into your calculator or you understand what that means, what number do you multiply by itself to give you 100? The answer is 10. So if you simplify the answer, even though it looks like a radical, it's actually a nice, pretty natural number. So it's a natural number, therefore it's a whole number. It's also an integer, and it's also a rational number. So subsets work inside out. Once you find the smallest subset, all of the other larger sets are included. I'm going to actually save number 2. Don't cross it off, but you guys are going to come to class tomorrow with number 2 finished. It's part of your homework or practice problem. The next section is solving equations. So I'm not going to read these to you. They're here. But it tells you the process in which we solve equations. So you might want to take a second to read those over. Okay? Inverse operations, you know that addition and subtraction are inverses, multiplication and division are inverses. There are more inverses than just those inverses that we'll discuss this year. Your answers, you can always check them by plugging them back into the original. You never want to plug them into any other form because if you change the form, that could have been your error right there. Answers are given in a solution set, those are little squigglies, or on a number line. So if you wanted to say that the answer was x is equal to 3, you could use set notation of 3, and then you can also find 3 on the number line, which I'm assuming is right here, and you put a dot. If there's more than one solution, you put more than one dot. We're going to solve the following equations. So we're going to use inverse operations. Before we can do that, though, we need to distribute, take care of some of these parentheses. So we're going to multiply both the y and the negative 2 by 3. And at the same time, we're going to multiply negative 2 to both of those terms inside those parentheses. So the 53 is just going to stay 53 is equal to 3y minus 6, because that's a 3 times a negative 2. And a negative 2, remember, keep that negative with the 2 when you distribute it. So I'm thinking of it as a negative 2 rather than a subtract 2. A negative 2 times a positive 3y is a negative 6y. And a negative 2 times a negative 1 gives me a positive 2. That's a difficult concept. People struggle with that concept. But as the year goes on, you'll see yourself making that correction. Before I start using inverse operations, I need to clean up this right-hand side. I see that there's 3y's here, and then I see a negative 6y's here. That means that they can be put together. It's called combined like terms. And so technically, I have 3y's sitting in one spot, negative 6y somewhere else. Really, all we have is negative 3y's. So when you combine like terms on the same side, you don't change symbols. You're just sort of sweeping them together, putting them in one group. I had a group of y's sitting here. I had negative 6 somewhere else, combining them, cleaning them up. And then I have negative 6 here plus 2 here really means that I have a negative 4. So now that my right-hand side is all cleaned up, I just keep bringing down 53. Try to align your equal sign. Try to keep that all nice and clean. Now I need to get the variable by itself. I need to solve for y. So you want to take care of the two things involving y. First thing we want to do is we want to add 4. You add or subtract first because it was the last thing that happened in the regular order of operations. So when I add 4 to both sides, we end up with 57 is equal to negative 3y. And then when we divide by negative 3, y is equal to negative 19. I can check my answer by plugging it into the original problem. I'm not going to bore you with that at this moment, but I know that my math is correct. So problem B to solve problem B, everything's cleaned up. The only problem is the 4/9. I'm not a big fan of the 4/9, so I'm going to actually make that 4/9 9 times bigger. If I make 4/9 9 times bigger, 9 times bigger means to multiply it by 9, it'll become a 4. But I can't just make one thing 9 times bigger. So I'm actually going to go through and I'm going to multiply both sides by 9, which means both terms get multiplied over there because you distribute. So I'm going to multiply everything by 9 to make things 9 times bigger. It's not a necessary step, but it's kind of a nice step. By doing that, 36m plus 45 is equal to 4. You no longer have to work with the fractions. So now when I subtract, I'm going to be subtracting a bigger number from 4. We subtract 45. 36m is equal to negative 41. When I divide by 36, m is equal to negative 41/36. It was going to be that way whether I left it as 4/9 or if I actually multiplied everything by 9. So you can't change the answer. The answer is going to be ugly no matter what. We can just leave the answer alone, but technically, whenever we have a solution, we're supposed to put them around it. We do it when we do inequalities, but with equations, for whatever reason, we stop doing it. Same thing with a number line. We could actually just say this is the solution. So those are two ways. The number line is sort of a picture of the answer, and then the set notation is just very technical, math technical. But introducing it to you here, just when we have to do it later on, you understand it. Same thing here. We could have put it inside the brackets, and then we could find negative 41/36 on a number line. I don't need to know anything else, and put the point there. All right, so your lesson summary. Usually what we do is at the end, I'll have you summarize, I'll have you put it in your own words or answer some type of question, not really mathematical, but more explanation-wise. So in this case, what's the major difference between a rational number and an integer? And I have two practice problems for you guys today. I want you to go back and finish example 2, and then there's more than one correct answer for some of them. So go back through your notes, find example 2, it dealt with the number sets, and then solve this equation. And you can just do that right in the space. If you need to fall out of the box and go onto your paper, that's fine too. But I'll be looking for your work, and I will be individually checking those notes when you come in tomorrow. Good luck.